Today, we are going to start from application of equilibria. And
Okay.
What is the benefit of this knowledge? Let's have a look. One of the application of equilibria is it is a Haber process. You can look this. This is a Haber process. This is. It is somewhat detailed, basically. Let's have a look. Equation involves, in Haber process, N2 plus H2 reversible sign. This is very important. Whenever it is asked to write equation, you will put reversible sign and NH3. Delta H is negative, means it is exo. Regarding reactants, if you look reactants, hydrogen, it is obtained by cracking of medium-sized hydrocarbon alkenes. And nitrogen, it is obtained from fractional distillation of liquid air. And these are the reactants, and from where we are getting these chemical substances. Next, come to conditions. Condition 450 to 600 degrees centigrade. This is, but we have to justify 450 RU to 600 degrees centigrade, or 400 even you can quote. When you quote this, any value of this range, there is a question raised. The reaction is exothermic. The reaction is exothermic, and it will drift the reaction backward. There will be no benefit of this high temperature, and we have to justify this. In this, the answer is there is triple bond in N2. In N2, there is triple bond, and triple bond has very high bond enthalpy. That's why to break this bond, we need high activation energy, and the temperature range that is quoted is not high, it is appropriate. This temperature range means the temperature, any temperature of this range, it is a compromise. It is a compromise. That's the word. It is a compromise because it is suitable to break N2. This is the temperature that you are providing. It is due to the role of catalyst. You need 450 to 600 degrees centigrade. If you're not adding catalyst, then this temperature, the temperature required to break N2, it might be about 1000 degrees centigrade. It means due to the participation of catalyst, this temperature is low. It is not too high regarding double bond in N2. So basically, it says, this is basically justification. Is it clear?
Yeah.
Basically, this is required. So it is said EA is higher, N2. The second point that you may quote, N2 is non-polar. That is also make it non-reactive. So this is also the provided temperature is necessary. Next is pressure. That is 200 atm to 50 atm. That is a huge pressure applied. Can you tell me the answer why this huge pressure is needed?
To favor the Ford reaction.
This is all right. The one justification is because forward side has lesser number of mole, so it favors forward side. There is also one more comment in this, and that is it's regarding Haber process. It's KC, or you can say KP, that is low. This value is low. The value is low, it means it is giving you the indication the product form at dynamic equilibrium, it would be less. Because Kc or Kp, it is the ratio of product concentration or pressure in terms of Kp over reactants. It means when you give high pressure, it will enhance the rate of reaction. It means the yield that is obtained at dynamic equilibrium, you will get earlier. You will get earlier. And you get high rate of reaction. It means the factor you are getting less amount of product at dynamic equilibrium, you try to overcome by increasing the rate of reaction. So this is basically, this is the point. Now we have a look this. High pressure is suitable. Now please look this. High pressure is suitable because the equilibrium yield of NH3 is low due to less value of Kc/Kp. In order to enhance the rate of reaction, the stated pressure is the requirement to make the process economical, because the rate of reaction is increased. And this is the justification. And these are the very important point. We are linking with equilibria and amount of product form. And this was the second factor, catalyst, that is iron. It lowers the activation energy. If you are not adding catalyst, it means might be 1000 degrees centigrade or greater temperature would be required. So this is the catalyst which brings the temperature lower, and this is. So this is the justification. Now, this is the diagram, simple diagram. If you from this side, this is a container, and this is a container. It is, and it is warm-up chamber, and then it goes into this. It needs some modification. Then it goes into the catalyst chamber. Basically, this is This is like this, catalyst chamber. This is catalyst chamber. And I remove this. This I remove. This is not. It goes into the catalyst chamber, where the reaction occurs. The extra heat, because the reaction is exothermic, extra heat we remove, and it is again transferred into warm-up chamber to warm the incoming reactant, like N2 is coming from this side, H2 from this, like this, is entering on this side, it is like this. Then it goes into the low pressure chamber, and from this it is shifted into low pressure chamber. It is this, and this low pressure chamber, there occurs an expansion. There occurs in expansion, and ammonia, due to the expansion, there it causes cooling effect, and ammonia is changed into liquid, and it drops down, and liquid ammonia is separated, and unreacted is basically, this is the container. If I this is linked with this. It's linked with this, basically this. Not this is wrongly made. I have changed this. So basically, unreacted N to H2, they are pushed through this pipe. This is unreacted. This is unreacted H2, N2 are drained into the warm-up chamber. And again, the cycle started. And this is the way. Now, when the reaction mixture is suddenly expanded, it causes cooling effect, and ammonia is changed into liquid ammonia, while H2N2 remain gas. Dear sir, can you explain why is it happening?
Because ammonia is more dense, so it sits at the bottom,
No.
or it dissolves into the, or it's condensed.
No. Should I tell?
Wait, what? I might have misunderstood the question. Can you repeat the question?
Should I? Actually, my question is, look, please, again. Again,
Yeah.
there is huge pressure in the catalyst chamber.
Yeah.
200 ATM, 250 ATM, 200 to 250 ATM pressure. That's a huge pressure. Now, this huge pressure, it means the gases are highly compressed. Yeah, it means in the chamber, this is into this chamber, gases are highly compressed. Gases are highly compressed. They are highly compressed because the pressure is huge. Now, suddenly, through this pipe, we bring into low pressure chamber. This is low pressure. Can you read this? This is written low pressure chamber. It means this chamber is a huge size, is having huge size. It means in low pressure chamber, gases will expand to their maximum, to the maximum. And expansion occurs over here. Gases expanded, and expansion occur over here. This expansion occurs over here, and while expansion, cooling effect occurs, and NH3 is changed into liquid. The question is, NH3 is changed into liquid, but H2N2 remain as gas. They are not changed into liquid, but ammonia is changed into liquid. Why?
I'm not sure.
I said, look, please. There are in the container, there are three gases. Mixture. This is basically the mixture, and this mixture is basically mostly it is unreacted H2 N2, because its value of Kc is low, or Kp is low, and small percentage is ammonia. Ammonia is, but it is in small percentage. Ammonia, if you look the structure of ammonia, and ammonia has one lone pair, and there are three bonding pairs. And you can look, N is partially negative and H is partially positive. Is it so?
Yeah.
When a molecule is having lone pair and it also has a partially positive hydrogen, it is capable to develop hydrogen bond. And hydrogen bond are strongest intermolecular forces. What happens over here, what is happening while compression in this chamber, when gases are close enough, hydrogen bonding are operating in ammonia molecule. Ammonia molecule are close enough. Now, when the molecules expand, because when you push them into low pressure chamber, molecules will go away from each other. Our molecules wants to go away from each other. For that phenomenon that molecules want to go away from each other, they have to overcome the attraction that is hydrogen bonding. Hydrogen bonding that's operating, it is like this. It is one ammonia, and this is another molecule. And it is hydrogen bonding are operating. And to break this hydrogen bonding, energy comes from the surrounding of the container. Because due to hydrogen bonding, the boiling point of ammonia is higher comparatively among gases. Among gases, it is higher. Its boiling point is about minus 34, minus 33. Its boiling point is minus 33 about. And due to expansion, that temperature drops about minus 34 degrees centigrade. It means due to hydrogen bonding, the boiling point of ammonia is higher among gases. That's why ammonia change into liquid. Because due to cooling effect, ammonia change into liquid. Boiling point means the temperature when the liquid changes into gas, and again at the same temperature, the gas into liquid. The gas into liquid. It means ammonia change to liquid, and it will separate it. You can separate from the rest of the gases. If all three gases remain as such, if ammonia, you are unable to change ammonia into liquid, you would be unable to separate NH3 because they are all gases. Regarding N2 and H2, N2, H2, they are nonpolar. They are nonpolar, and nonpolar have IDID forces, or you can say London dispersion forces or van der Waals forces, and they are weak forces. That's why their boiling point is quite low, quite low. While expansion, the temperature of the chamber, this container, drop about minus 34. But ammonia boiling point is minus 196 degrees centigrade. It means, N2. N2 boiling point is minus 196, and H2 is about minus 240 roundabout. It means these both gases remain as such. They will not change into liquid. That's why we can push them into from this container to the warm-up chamber, and ammonia being liquid drop down. And this is written over here. Let's have a look. Gases expanded in low pressure chamber, temperature dropped to minus 34, NH3 boiling point is minus 33, so it will turn liquid. While N2 is boiling point is minus 196, and H2 that is below minus 200, means about minus 240 roundabout. The excess N2H2 sent back to warm-up chamber along with X means heat, you can say. There's no need to write heat over here. Basically, a warm-up chamber, and to start the cycle again. There's no need to. This is. Dear sir, is it clear?
Yeah.
So, can you repeat this, what I said? Why ammonia change into liquid?
Due to the lower pressure in the chamber, so the gases aren't as there's not as much. The gases are able to expand, which allows them. The other unreacted gases are able to expand, but the ammonia just sits at the bottom and condenses.
I write over here too, so that it should be more clear. Basically, ammonia has higher boiling point. I'm writing BP short, but you write complete wording, not BP. Has higher boiling among gases. Gases. Due to hydrogen bonding hydrogen bonding operate in molecule operates among molecule. Ammonia has higher boiling point among gases due to hydrogen bonding operate among molecules are operating among molecules due to expansion due to expansion energy of the surrounding in the container is used up to overcome hydrogen bonding which drops temperature about which drops temperature about minus 34 degrees centigrade. Ammonia NH3 changes into liquid at about minus 33. So separated. So this is the reason. Next is Haber process. And Haber process and this is all written, you can go through as well. Next is a contact process. Contact process is method to produce sulfuric acid commercially. What are the stages involved? Burning of sulfur or sulfur-containing ore, or you can say roasting of ore. Sulfur plus O2, SO2. Second point, SO2 is purified from impurities. These impurities make catalyst ineffective, or catalyst gets poisoned. This is the word we use. Catalyst gets poisoned due to impurities. That's why it is compulsory to remove impurities. And point 3 is point 3 is purified SO2 pushed into catalyst chamber. And what are the conditions? What are the conditions? Let's have a look. This is condition. Number 1, temperature. Temperature is 450 to 600 degrees centigrade, very high temperature. Now you have to justify. Contact process is also a commercial method. This temperature range is appropriate because to maintain appropriate rate of reaction. Furthermore, at low temperature, catalyst does not work. And this is the justification. Now, pressure is 1 to 2 atm. Now, as I look carefully, over here we are going to apply 1 to 2 atm pressure. But in case of Haber process, we are using very high pressure. Why?
Where?
In contact process, we are using, in Haber process, we are using 200 to 250 atm. Very huge pressure. But in contact process, we are using 1 to 2 atm pressure. That is low. Why?
To prevent the reaction from being reversed.
No, look, please. This is the equation. Now, please look this. This is the equation involved in catalyst chamber. In catalyst chamber, in have a contact process, catalyst chamber. This is sulfur dioxide and O2 from air is forced into the catalyst chamber and you get SO3. If you balance this, you put 2 and 2. Number of moles on the reactant side are 3. On the product side, this is 2. High pressure is suitable in this case, like in Haber process. But we are applying low pressure instead of high pressure. Why?
Yeah, to prevent it from reversing the products back to SO2 and O2.
No, because if you see the profile, reactants are more in moles, product are less. High pressure is suitable. High pressure favors forward side towards lesser number of moles. But over here, we are applying low pressure. Like in Haber process, if you look this, in Haber, if you compare this equation with the Haber process, in Haber process, if you compare this in Haber process, This is the equation. If you can recall, this is the equation. Number of moles, a 2, and this is 6. Reactant side are 4. Product side is 2. The trend is same. Reactant side have more moles, product side are less. But in Haber process, we apply 200 atm atmosphere to 250 atm. That is huge pressure. But in case over here, we give 1 or 2 atm. This is the question. No, look, please. The reason is it's KC or KP. Its value of KC or KP is higher. When you say the value of KC or KP is higher, it means you are saying the yield at dynamic equilibrium is more. Means maximum reactants are changed into product at dynamic equilibrium. Product are maximum, have larger proportion. No doubt, if you give high pressure, it will favor forward side, but it will increase the cost of production, because to bear high pressure, you need very sophisticated, very modernized equipments to bear heavy pressure. And there would also be maintenance. There will be more maintenance due to wear and tear in the machinery due to high pressure. Over here, this even at low pressure, you are getting high yield because the yield at equilibrium of the product is appropriate. Means about more than 60% you convert more than 60% your reactants are changed into product. So this is the reason to make the process economical. We prefer pressure should be low because the due to the higher Kc or Kp value. Now I read this. Look, please. Low pressure is feasible because the yield at dynamic equilibrium is appropriate. Means in ammonia, the yield is less at dynamic equilibrium. Over here,